control limits. Although the point may be falling within the control limits, but they have to look critically, because these are the average control limits and these are not the accurate control limits. Then the third one is the draw several sets of control limits. We may have supposing 3 different subgroup sizes. So, for each different subgroup size we will be having different upper control limits and different lower control limits. So, supposing this is the subgroup, this is the lower control limit based on 50, this is the lower control limit based on the subgroup size of 100, and this is the lower control limit based on the subgroup size of 150. Accordingly, 50, 100 and 150, and for each subgroup size we will be plotting the points keeping in mind these 3 control limits. So, these are the 3 options we are having for dealing with the situation when the subgroup size varies. Now, the choice between P chart and NP chart. As we know that P chart is fraction defective chart and NP chart is number of defectives. So, in the P chart we plot fraction defectives, in NP chart we plot number of defectives. Now, since we are plotting number of defectives, so the limitation of NP chart is that it can only be used in situation where sample size is constant. If the sample size varies, we are bound to use P chart, but in case it remains constant, we have the option to use either NP chart or P chart, but the limitation of NP chart is that it can only be used where sample size is constant. Now, the NP chart, it is the number of, we may also call it as number of defectives chart. Now, the mean of the NP chart is NP bar. We know that the value of P bar is equal to sigma Ni Pi divided by sigma Ni. We have already calculated in the previous case. Now, the standard deviation of the NP chart is equal to under root NP bar into 1 minus P bar. It is also known as Q bar. P bar is the fraction defectives, the probability of occurrence of the defectives, and Q bar is the probability of occurrence of the good items, non-defective items. Now, the upper control limit of the NP chart is NP bar plus 3 under root NP bar into 1 minus P bar, and the lower control limit of the NP chart is NP bar minus 3 under root NP bar into 1 minus P bar. So, the same methodology will be used for drawing the control charts of NP chart. The control line will be drawn, center line will be drawn, sorry, of the NP chart. Upper control limit and lower control limit will be marked, and with reference to a particular sample we will be plotting the points of NP. Now, the difference is we are plotting the NP, the number of defectives, and not the fraction defectives, and then finally we are going to join these points by the lines. So, this will be the number of defectives charts. Any point falling outside the control limits will represent that it is not conforming, it is representing that statistical control is not there, and we have to deal with this situation because assignable causes of variation are present, and it is because of some external source of chances are there because of which this problem has occurred. Then the essential steps in the control charts. The first is we record the data generally in the tabular form, like samples 1, 2, 3, then the defectives against each sample and then the sample size. So in this tabular form we are going to record the data. This is the first step. Second step is we compute the value of P, value of P bar. This is P I, this is P 2, this is P3. So P bar will be sigma NP divided by sigma N. Then P bar is then the third is we determine the upper control limit and then the lower control limit, and then the last step is we plot the points on the control chart. Now when we plot the points initially on the control chart, these are known as trial control limits. Because we are plotting these points in the raw form and we do not know at this stage that whether the process is under statistical control or not. If all the points are randomly distributed and falling within the control limits, we will use these control limits as the final control limits, but till date we actually find out that all the points are falling within the limits and process is under statistical control limit, we cannot say that these control limits will become our final limits. So these are the at the initial stage are known as trial control limits. Any point falling outside the control limit will be deleted from those particular calculation, and then revised control limits are determined, and finally these steps are continued till we get all the points within the control limit and process becomes within statistical control. Then those particular control limits and the P bar value becomes our final values. Then comes the U chart or the C chart. It is based on the fact that we have to deal with defects now and not defectives. Now what is the difference between a defective term and a defect term? An item is said to be defective if it fails to conform to the specifications in any of the quality characteristics. If an item fails to conform to the specification in any of the characteristics, it will be termed as a defective piece, whereas defect is each characteristic that does not meet the specifications is a defect. Supposing we have casting and number of defects may be present in it, like blowholes, like spots, like any kind of cold spots which are present on that particular casting, and that kind number of defects will not be able to make it a defective piece till all the defects are within the control. So this is the difference between defect and defective. A number of defects present in a product will not make it a defective till if any of the quality characteristics which it fails to conform to the specification becomes a defective. So we deal differently with defect than defective. There are certain applications where only control chart for defects can be used. The examples are like number of surface defects on the photographic film. The second is number of defective rivets in the aircraft wing. The third is number of surface defects observed in the galvanized sheet. Fourth is number of breakdowns at a weak spots in insulation in a given length of insulated wire. Then it may be the number of small air holes in the glass bottles. Then it may be the number of imperfections observed in the cloth of the unit area, or it may be the number of defects such as blowholes, cracks, undercuts in the casting or in the welding piece, or it may be the total number of defects of all types of complex assemblies like sewing machines, like tractors, like radios, etc. So in this case we have no other option but to use the control chart for defects. We have two types of charts under the control chart for defects. The first is C chart and the second is U chart. Then the control limits for the C chart are based on the Poisson distribution. The Poisson distribution is satisfied when two conditions are met. The first condition is that the area of opportunity for occurrence of defects should be fairly constant from period to period. For example, while inspecting the imperfections of a cloth, it is necessary that the same area may be used, supposing 100 square meter. Then the another example may be the number of paint imperfections per square meter of a painted surface. Then the second point which should be met for Poisson distribution is that opportunities for defects are large, while the chances of defect occurring at a one spot are small. Then the example may be the consider a case in which the product is large units, say a radio or the TV, which have defects at a number of points, although one point has only few defects. Then the mean and the standard deviation in case of C chart. Mean is C bar, it is sigma Ci divided by n. Ci is the number of defects in ith sample, Ni is number of items in ith sample. Then the standard deviation is under root C bar. Upper control limit in case of C chart is again based on plus minus 3 sigma limits, that is C bar plus 3 under root C bar. Lower control limit is C bar minus 3 under root C bar. The same methodology is used. We show the center line with the solid line. For the C chart, upper control limit is the dash line. Then the lower limit is again chain line for C chart, and then we plot the value of C's against each subgroup. Then finally we join these with line. The point falling outside will indicate that the process is not specifying the statistical control, and it will represent that some assignable cause of variation is present, and we have to hunt for the cause of that particular assignable cause of variation. Similarly, in case of U chart, we have first the sample, it may be, then the sample size, then the number of defects, then we calculate the UI. So supposing size may be 10, which remains constant. Now number of defects may 2, may 3, likewise. So here it will be 0 0.2, 0 0.3, 0 0.2. So sigma UI, U bar will be sigma UI divided by capital N. So standard deviation of the U chart is under root U bar divided by N. Upper control limit is U bar plus 3 under root U bar divided by N, and lower control limit is U bar minus 3 under root U bar by N. Now we are going to cover an example. First we will take the example of control chart for defectives, that is P chart, in which we have 20 samples, that is capital N is equal to 20, and the sample size is 200 each. It means that the sample size remains constant. Then we will first of all tabulate our data. Sample number number of defectives, then we are going to calculate the fraction defective. Supposing 9 number of defectives are present in the first 7, then 14, then 15, 8, 7, 9, 11, 16, 12. Then since the sample size is 200, the fraction defective in the first sample will be 0.045, then it will be 0.035, then it is 0.07, then it is 0.075, then it is 0.04, then it is 0.035, then it is 0.055, then it is 0.080, then it is 0.060, here it is 0.045, then it is 0.055, then it is 0.080, then it is 0.06. Then for the sample size of 11, 12, 13 and up to 20 we have the data. Then we calculate P bar. The total number of defectives are calculated. This is sigma NP, 9 plus 7 plus 14 likewise. So it will be sigma NP divided by sigma N. Now sigma NP is 240 and sigma N will be calculated from the total number of samples. The first sample size was 200, second sample size was 200, so total number of 20 samples were there. So it means that the sample size is 200 multiplied by 20. So it comes out to be 0.06. As we know that upper control limit of P chart is P bar plus 3 under root P bar into 1 minus P bar divided by small n. So it will be 0.06 plus 3 under root 0.06 multiplied by 0.94 divided by 200. So it comes out to be 0.1104. Similarly, lower control limit of the P chart comes out to be 0.0096. Now we are going to plot the control chart. Since P bar is 0.06 and upper control limit of the P chart is 0.1104 and lower control limit of the P chart is equal to 0.0096. So for each sample we are going to plot. So for the first sample P1 was 0.045, So 0.045 will lie somewhat here. For the second sample, the P value was, fraction defective was 0.035. So 0.035 will again lie somewhat here. Then for third sample, the value was 0.07. So it will lie above the center line. So in this way we are going to plot all the values, and we will find that in the 11th sample we had the number of defectives were 26 and fraction defective was 0.13. So this particular reading of 11th will be lying outside the upper control limit because it is 0.13, which is greater than 0.11. So this indicates that the process is out of statistical control. So these are the trial control limits and these are not the final control limits. So we need to revise these. How we can revise them? We will be calculating the mean fraction defective again. It will be calculated by subtracting 26 from 240 divided by, now only 19 samples are there, so it will be 0.056. Again we are going to calculate the revised upper control limit of the P chart and lower control limit of the P chart, and then again we will be plotting the control chart and we will find whether all the points or the fraction defectives lie within the control limits, and we are not going to include the value of the 11th sample. So without this particular value of 11th sample, we are going to again plot, and if all the points lie within the control limits, then only these control limits will be categorized as the final control limits of the P chart. So this is one example of the P chart. Then for the example of control chart for defects, we take another example. In this, the factory producing the spark plugs, the number of we take another example in which we have the data in the form of number of samples is equal to 10, and for each sample the sample size is 100. We have the lot number, and we have the number of leaks in a radiator. We have 15 leaks in the first sample, then 17, then 12, then 16, then 14, then 5, then 14, then 11, then 9, and then 10. And we are going to calculate the value of U. It is 0.15, 0.17 likewise. Then we know that we can calculate sigma U by totaling all these values, and U bar will be equal to sigma U divided by N. Sigma U comes out to be 1.23, and we know that number of subgroups is 10, so U bar is equal to 0.123. Similarly, upper control limit of the U chart will be U bar plus 3 under root U bar by small n. So it will come out to be 0.228. Lower control limit of the U chart will come out to be 0.018. So in the same manner we will be plotting the chart, and any point goes outside the control limit will mean that these control limits are only trial control limits, and it will need to be revised. So in this way we can determine whether our control limit are trial control limit or final control limits. If all the points are lying within the control limits, then it will be these will be final control limits, otherwise that particular value will be deleted from our calculation and revised control limits will be designed. So dear students, I hope that you must have gained from this particular lecture control chart for attributes. Thank you.